Okay. So, in the last class we looked at a system which is called default logic, but basically which was logic augmented with a set of default rules. The problem with the default rules was that they were not sentences in logic which you could manipulate otherwise. So, for example, you could not choose a contrapositive of a rule which would say, for example, that if it cannot fly, it is not a bird essentially. So, the rule is that a bird can fly, the contrapositive would be if it cannot fly, it is not a bird. So, those kind of things you cannot do, because that is not really part of the logical statement essentially. So, today we want to look at something called autoepistemic logic. Which tries to put the whole thing in logical behavior. So, in that sense it is similar to circumscription, that it is sort of tries to simply deal everything logically, but circumscription had this thing that you were talking about minimal models essentially, that you said that only for the smallest extensions of certain chosen predicates, whatever you can infer essentially. Here we take an approach which is similar to that in default logic, which says that if it is consistent to believe in something, you believe in that thing, and then try to work with this essentially. In the process, we will introduce a new operator called a belief operator. It is a modal operator. We have not really looked at modal logics too much, but here is a chance, I think. So, if you say B alpha, where alpha is any formula, then B alpha stands for that you believe alpha essentially. And in the treatment that we are doing today, there is only one agent. So, essentially it is the agent's beliefs that we are talking about, but in the next class we will talk about multiple agents, where if there is more than one agent, then what do they know about what the other agents know and that kind of stuff essentially. So, B alpha basically stands for the fact that agent believes in alpha. It does not necessarily mean that alpha should be true. Okay. It only means that the agent believes in alpha essentially. If we say not B alpha, then we say that this says that agent does not believe alpha. On the other hand, if I wrote B not alpha, this would mean that the agent believes in not alpha, where not alpha is treated as a formula essentially. So, there is a difference between not B alpha and B not alpha essentially. So, not B alpha simply says that the agent does not believe alpha, and B not alpha means that the agent believes in not alpha essentially. And we will see that this will be associated with consistency, that it will be tied up with consistency essentially. So,
not believe not alpha?
it means that the agent does not believe in not alpha. You have to just break it down, I think. So, let us go back to the Tweety example and see how you would state that in this particular logic. So, we could write it as follows, that any bird that can be consistently believed to fly does fly. This is basically our basic idea behind default reasoning. So if you say football players are rich essentially. So, essentially you are saying that as long as you can consistently believe that if x is a football player, x must be rich, unless you can show otherwise essentially. Or here we are saying birds can fly, is that if you can consistently believe that birds can fly, then the bird does fly essentially. So, that is the assumption that we are adding. So, this part we can replace by another statement, not believed to be flightless. So, the rest we can copy. Any bird not believed to be flightless thus fly essentially. So, here if I again break this down, flightless would be represented by not flies x, believe would be replaced by the belief operator and not would be negation exactly. And this any bird will kind of correspond to for all x if x is a bird, and this does fly will correspond to flies essentially. So, in autoepistemic logic I will write the following statement: for all x bird x and not believe So, where and of course, has priority over this thing. So, we can put a bracket if you want. So, if x is a bird and you do not believe that x does not fly, then x flies essentially. So, if we have this sort of a statement and if you have knowledge about many birds, so we will take work with the same knowledge base that we were talked about earlier, where Tweety can fly and Chili cannot fly. So, we know that Chili cannot fly, but we do not know anything about Tweety, and we will be wanting to infer that Tweety can fly essentially. In the same kind of a thing we would want to do. But now, essentially the task is to arrive at a stable, what is called as a stable set of beliefs. Which means that we want to give truth values to various belief statements essentially, and which belief statements which occur basically in our knowledge base. So, we have only one knowledge base, which is now in a modal logic called Autoepistemic logic, which apart from the normal predicates like bird x, man x, mortal x, flies x and so on, also has this B operator, which says that you take any statement and you put B in front of that, it means that the agent believes in that essentially. So, let us now talk about stable sets, and essentially if we can find a stable set of beliefs, then whatever is entailed by this set of beliefs we will be willing to believe in that essentially. That is the basic idea. So, what is a stable set, and the term that we use is an expansion of the KB. It is like extension, it is just that we are using a different term here, expansion. So, if a KB has a set of statements with the B operator, we are interested in a reasonable set of that is a question we are asking all the time, that given this knowledge base, what is it reasonable to believe in essentially. And now we are saying here that here in autoepistemic logic, anything that follows from a stable expansion, which means we will add some statements to the knowledge base in the style of default logic, but except that we do not have those separate default rules, we have only these belief statements in our logic system. Based on that, we will add certain statements, and then we will define a notion of stability, and if a expansion is stable, then anything that follows we will accept as something to be this thing. So, we call a set stable. So, we will use epsilon again if the following holds. So, there are three properties. One is closure under entailment, which basically says that if the expansion or the set entails a formula alpha, then it must belong to the extension. So, it is closed under entailment. If you can derive something, then you should add it to your set of beliefs essentially. 2 is called positive introspection, and this says that if some formula alpha belongs to your extension or expansion, then belief alpha also must belong to the expansion. This is a property of stability essentially. If you believe in some, if your knowledge base or if your set of beliefs has a statement alpha, then B alpha must also be in your set, which also means that B B alpha should also be in the set and B B B alpha should also be in the set. So, it will carry forward indefinitely of course, but we will not work with infinite sets of formulas. We will try to restrict our belief operators to only what are called as objective sentences, which are believe in an objective sentence essentially. In the next class, maybe when we talk about multiple agents, then we will say that I know that you know that kind of a thing there. So, I can say for example, that I know that you know that the end semester is approaching or something like that essentially. But here we will restrict our depth of beliefs to only maybe one, at least for these examples essentially. And the other thing is called negative introspection. This says that if alpha does not belong to the extension, then not belief alpha should belong to the extension. And if you go back to the statement that we wrote about birds, the statement said that if x is a bird and if you do not believe that x does not fly, then x flies essentially. And you can see that negative introspection will come into play here to establish this consistent belief, that if you cannot show that, for example, Tweety cannot fly, then you can add that you do not believe that Tweety cannot fly essentially. And if you can then add that sentence, then you can use this formula here to conclude that Tweety can fly essentially. So, that is a basic idea, except that now we have posed everything into a this thing essentially. So, the sentence that we will be interested in is not belief, not. If you could add this sentence to our expansion, then because we also have, so let us say we are talking about Tweety now, then if we have bird Tweety, and if we can add this, then you can see that we can infer that Tweety can fly essentially. So, that is going to be the general idea essentially. So, we say that alpha is a stable expansion of a KB if and only if for every phi which is in that expansion, the following holds, that phi belongs to expansion if and only if the KB union you can add all the belief statements where if alpha belongs to the expansion, you can add belief alpha to the expansion, and you can add not belief alpha if alpha does not belong to the expansion. So, the union of these three sets entails phi. You can see the similarity with default logic, essentially KB union some delta entails phi, except that in this case the assumptions that you are making are about those belief related statements. So, all kinds of belief statements, whether they are true or whether they are false essentially. So, you can add a belief statement if you know that alpha is in the knowledge base, you can add belief alpha. If you know that alpha cannot be derived in the knowledge base, then you can add not B alpha essentially. Now, the way that we will go about is to guess a set of belief statements and check if it is a stable set. Actually. And as you know, whenever we say guess, we essentially mean search through. When you come to implementation. So, that is going to be our approach, that we will try all combinations of belief statements. So, in a knowledge base there will be a finite amount of belief statements, especially if we have restricted ourselves to saying that the belief statements only apply to what are called as objective facts, basically which are statements which do not have the B operator. Then there is only one level of nesting allowed. So, there is only, and there is a finite amount of individuals we are talking about. So, there will only be a finite amount of belief statements that we can make. So, for example, if you are talking about birds can fly, if there are 3 birds in our knowledge base, we can have only 3 belief statements about those 3 birds. So, which means each of them can be true or false, which means 2 into 2 into 2, which is 8 combinations we will have to explore and see which of those combinations is stable essentially. So, let us first write down the algorithm at a high level. And then we will see an example. So, we assume that statements are either objective which means without or of the kind B alpha, where alpha is objective. Okay. So, just for simplicity we are assuming that we are not going into deeper levels of belief, that I believe alpha, I believe that I believe alpha, I believe that I believe that I believe alpha, all those things we are not really interested in here, because our logical rules that we are using uses only these kind of statements. If we had statements which had rules about belief of belief, then maybe we would have to go to that level. But since the bird knowledge base that we are talking about has only this statement that if you believe that the bird, if you do not believe that the bird is flightless, then you can assume that it flies essentially. So, we will stick to that essentially. So, the algorithm then is replace each belief alpha I in the KB either true or false. So, essentially we will try out different combinations and then you simplify and call the resulting KB as KB prime. So, what do we mean by simplify? It means that if you have a statement of the kind B P implies Q, then there are two cases. If B P equal to true, it will take us to true implies, I am just using some very informal notation, true implies q. So, maybe I should just put this in bracket and say is equivalent to, which is equivalent to q basically. So, if B p I am going to replace with true, then true implies q is basically q. If B p is equal to false, then this will become. So, let me use this arrow here to see that it gets transformed into this. False implies q, which is equivalent to true. So, it is basically like adding a truth to the knowledge base, which is meaningless. So, it basically that sentence, that statement vanishes. So, we have a statement of the kind B p implies q. If we choose B p to be true, then it simplifies to q. If we choose B p to be false, then the sentence just vanishes, because it is replaced by true essentially. So, that is what we mean by simplify. Then if B alpha I was replaced by true, confirm. So, we want to basically test whether the thing is stable or not. And likewise, if it was replaced by false, confirm that it does not entail alpha I. That is those are the conditions for stability, the positive and the negative introspection. If condition confirmed for every B alpha I, then K be 0. So, essentially in generating the stable expansion, what we are doing is we are removing the belief statements in such a manner that we end up with a stable expansion essentially. So, either we are replacing the belief statements with true or belief statements with false, and then checking whether it is a stable expansion or not, and then replacing that. So, let us look at this example now. So, essentially we have two belief statements, one about Tweety not flying and one about Chili not flying essentially. So, let us just look at the four possible examples here one by one. So, case 1, this belief So, I will just use T for true and belief not flies chili is also true essentially. That is the first case where both the belief statements are true. So, the knowledge base will have the first three statements always, which is bird Tweety, bird chili and not flies chili, plus two more statements which we have to simplify. In this case, because we assume this to be true, its negation is false. So, bird Tweety and false is false. So, false implies flies Tweety is true. So, both the statements will vanish. So, the KB 1 let me call it is equal to KB. Okay. Or KB let me call this KB 2 is equal to KB 1, and when I call this as KB 1, both the other statements vanish. But now we have to verify that it is a stable expansion. To verify that, confirm that the knowledge base 2 entails not flies Tweety. That is a step that we have to do to verify that the expansion is stable essentially. So, we should be able to show that not flies Tweety is entailed by the knowledge base, and likewise for the other one, which is not flies chili. Now, not flies chili of course holds in the knowledge base because it is given to us, but this is this test fails. So, it is not stable. The positive introspection does not happen here. So, case 2, so if we do this, then this will result in that corresponding statement being reduced to bird chili implies flight chili. This will go to KB 3 let me call it. So, this will simplify when you say that belief that the chili does not fly is true, then it will reduce to this KB 3 and that will result in this thing essentially. So, you can see that here confirmation fails for both. So, this as well as this essentially, neither of the beliefs will lead to a stable statement essentially, and as you can see you will end up concluding that chili can fly, which is obviously a contradiction. Let us assume that both are false. So, this fails here as above. So, not stable. This is also not stable. So, finally, case 4, believes not lies Pt is equal to false and believes not lies is equal to true. Now, observe that here in both these cases this statement reduces one element in the knowledge base to bird Pt implies flies Pt. I will just write this, it is added to the knowledge base essentially. And this is a stable expansion. So, I will leave this for you to verify that this is a stable expansion, because you have assumed that bird that belief that Pt does not fly is false, which means its negation is not in the entailed in the knowledge base. So, it is fine. And because we can now once you substitute false in the original statement, we get this statement that bird Pt implies flies Pt, and because we have bird Pt in the original knowledge base, we can now add flies Pt to the knowledge base in the stable expansion essentially, and not flies chili is anyway in the stable expansion. So, this is the only stable expansion for this thing essentially. So, there are some interesting cases which I will ask you to look at. If it is right. Like before. So, if we have something like belief P implies not P, you should verify that it has no expansion essentially. Then if we have a set of two statements, belief P or belief not P, not belief P implies Q and not belief Q implies P, has two stable expansions. One in which P is true and the other Q is true. And you can see that these are the only two stable expansions. Basically, you will have to look at the 4 combinations of this belief statement essentially, and you will see that out of those 4 combinations 2 are stable and 2 are not stable. In one stable combination P will be true, in the other stable combination P will be true. And finally, if you look at a statement like this, which is similar to what we saw in default logic. Unfortunately, here also this has two stable expansions. There are two possible expansions, one in which belief P is true and one in which belief P is false. Both of them unfortunately are stable essentially, and this is again a little bit of counterintuitive thing essentially, because what are you saying here? You are saying that if you believe in P, then P is true essentially. There is no real evidence for P to be true essentially. Nobody has said that P is true, it is not part of the knowledge base or any such thing. You are simply saying that if you have a knowledge base like, if you have a statement like this, then it can lead to this kind of imaginative belief essentially, that you can simply believe in it by saying that you believe in it essentially. But that is a problem that this kind of reasoning does involve essentially. So, I will stop here, and in the next class or in the next couple of classes we will look at the scenario where there are multiple agents. So, where agent A knows something and agent B knows something and agent C knows something and so on, what kind of representation and reasoning is useful there essentially. So, you should be able to make statements like John knows that Mary has the book, and but Mary does not know that John knows that Mary has the book, that kind of statements. How can we represent and what kind of reasoning we can do with that? We will look at some interesting examples in the next class. So, I will stop here.